Okay, so let's get started here. So we'll begin today by doing or finishing up the test number 2 review. Then we will get into chapter 6. Obviously, test number 2 is on Thursday, and project number 5 is due Tuesday, November 27th. Are there any questions before we get going here?
A couple questions about the project.
Yes.
In question 2, part C, where we just increase the number of observations for our data sets, do you want to see all of the same code again when the only thing that's changing is n at the very beginning, or do you just want to see the results?
It would be okay if you don't show me, I guess, some of the code that's just exactly duplicating. I mean, at least the way that I wrote my code was I could just simply use a different, I had an argument for the sample size that I could pass through a function. So I just had myself running the same function, but with just a different n.
Okay.
Did you have more?
Yeah. The other one was in part D, the third one where it says verification that the data was simulated correctly. What are you just wanting to see that the mean and the variance are showing up the way we want them to, given our distribution?
Yeah.
Okay. What verification are you looking for? Visual, numerical? Okay. Thank you.
Yeah. Any other questions? Okay. So let's then talking about the test. So there will be virtual office hours. Tomorrow night from 9 to 10 p.m. In the chat room. So if you have any last-minute questions, please feel free to stop by. The test itself will, of course, start at 4 p.m., but I will be here until 5:30 p.m., so if you like a little extra time, you can have it. Again, the test is over basically chapter 3 through 5, with a little bit of chapters 2's double bootstrap part, which kind of overlaps the stuff that we did in chapter 3 with double bootstrap. So in terms of the test layout, there's 100 points possible. And number 1 is worth 26 points. It has 3 parts. And involves you're going to have to write a calc.t function to do some stuff as well. Number 2 is worth 17 points. 2 parts. And you get to derive something. Number 3 is worth 36 points. 4 parts. I'm sorry, 5 parts. There's going to be some R, and there's going to be a calc.t function that you're going to have to calculate or construct again to do some calculations. And lastly, number 4 it's worth 21 points. And it's the short answer questions. There are 4 parts. So 4 short answer questions. These questions are not necessarily connected in any way. You like to provide a few sentences or do some small derivations. And last, I guess, as well, number 5, it's 2 points extra credit. So I gave a test in my Stat 70 class today, and I had an extra credit problem on it. And the question was, what year did Reggie Miller be inducted into the Basketball Hall of Fame? We happened to talk about this NBA guard dance, so it made sense. It didn't. And then one of the great news today, seems like there's just a large number of people who are getting the answer right. It's 2012. Well, maybe a lot of good or a lot of basketball fans out there who've been paying attention to this, or perhaps what they've been doing during the test is Googling it and figuring it out that way. The reason why that's my working hypothesis right now is because someone says September 7th, 2012. Now, I don't think there's any really that strong basketball fans in the class that would know September 7th, 2012. So, anyway, please don't Google it. If it's Googleable. I don't remember what I put there for the exam for the question. Let me just double check. Sorry.
Is it Google?
It is, yes. But don't do it. But it corresponds to something that was mentioned during class. So, anyway. So that's the general layout for the exam. Now again, with the exam, there's the formula sheet and the notation sheet that you can take a look at on the test webpage. I will give you a copy of that during the exam. The test structure is the same as before. I'll give you the test on paper, and you'll need to write all your answers on there. We're using the computers in front of you basically as a calculator to do the various calculations that are needed. When a question requires you to use R, simply write the numerical result that you get from using your computer, write it on the test. But you also need to show your work in some way. And typically what this means is actually show me the formula in terms of the mathematical equation that's used to do the calculation. If there's time, and only if there's time, you can also put some of your R code down, but that is not a requirement. Test is obviously closed book, closed note. You'll have access to my R programs on my course website, just like last time. Okay. Are there any questions? That's all I had to say. I was left to talk about the exam. Okay.
It was when we revised the empirical input for the influence function. Yeah. And so down, I guess when I did it, I just separated it, and I did, so keep low this for the second one, for the second sample. And you, I pulled it right
Right.
there you go. So you just took the entire quantity and took the inverse of it and so forth. Whereas I started with the same kind of format that we had for number one,
Mm-hmm.
and then use the formula where it's like take the derivative of all of t of n with respect to t of n, t of 1, t of n. It just seemed like you did it a different way.
I'm not necessarily following you, but perhaps this is what you're saying. You had something like this. And you actually did the derivative here. Is that what you're saying, where you did it all at once? Or
No, I'll think of a better way to, I'll just go to your chapter and specify it.
Okay. Okay. There's multiple ways to do this problem. I did what I thought was the easiest way, which was to derive, these separately. But you can kind of do it all in one shot too, versus doing things separately. Anyway. Were there other questions? Okay. Let's continue in Chapter 6 then. Of course, this is not on the exam. Okay, so we're going to talk about regression analysis and how the Bootstrap can be used with it. We're just going to be talking about, I guess this regular old regression analysis, meaning that the epsilons have a normal distribution, so y has a normal distribution. We have a constant variance as well. But the stuff that we're going to talk about here will give you the background on how to approach more complicated models, such as generalized linear models. There is a Chapter 7 which talks about generalized linear models in one section, but unfortunately we're not going to be able to get to it. But this will set you up for more complicated kinds of models out there. So just to review what a regression model is, this is more just so you get used to the notation that our book uses. So we're going to start with just a simple linear regression model. So we have one explanatory variable, x, is trying to predict y. Our observations are j equal 1 to n. Epsilons are I, d, normal, 0, sigma squared. So of course, one can come up with least squares estimates for these betas up here. Here's beta hat 1. Nothing new there. Maybe you haven't seen this though before. You can actually simplify this a little bit more so that you just have y sub j over there. And that y bar disappears. You know why? How about you multiply this part right here times yj, then minus, then the sum, this part again, times y bar. What happens to the y bar? Comes out the sum, or factor out the sum, so you're just with the sum xj minus x bar, which of course is 0. Just a little simplification. This will be useful later for some of our derivations that we will do. Notice that what we normally think of as y hat in most classes is actually denoted by mu hat here. The reason being is because we're basically getting, let's say, the expected value of y hat. So there's mu hat there. Here's my residual. Of course, the sum of the residuals is 0. We're going to look at some residuals shortly that don't have a sum of the residuals being 0 anymore. Our estimate of sigma squared is our mean square error. Our book would denote this by s squared. Of course, beta hat 0 and beta hat 1, the estimates, or estimators, I should say, are unbiased. And we have corresponding formulas for the variances that we can also derive too. These beta hats have normal distributions. You can easily show that because of the y's having a normal distribution and the epsilons having a normal distribution. The expected value of your residuals are 0. The variance of a residual is sigma squared times 1 minus h sub j. Notice again, it's not just simply sigma squared. You have to worry about the hat matrix diagonal value. That's h sub j. So does anyone know why the hat matrix is called the hat matrix? Well, since I'm teaching regression right now, this is what I have to remind my students many, many times, because the hat matrix H puts the hat on top of Y to get to Y hat, the hat matrix. So again, H sub J is the jth diagonal value of the hat matrix. We're going to be talking about things called modified residuals. So notice it's just your regular old residual, so E sub j, but now we're going to divide by 1 minus h sub j square root. And the reason being is because these r sub j's will have a constant variance. Notice how the variance of E sub j changes depending upon what h sub j is. So if I take out that 1 minus h sub j, kind of divide the residual by that, the square root. Now I have a constant variance for r sub j, my modified residual. This is going to be helpful when we do resampling, because we want to be resampling, as you will see, we want to resample stuff that has the same distribution. Okay? Note though, by dividing by this hat matrix diagonal value, notice that these modified residuals do not have a mean of 0. And the reason why is you can see that this h sub j screws things up. Okay? So in the end, actually what we'll be doing is this. We will be resampling rj's minus the r bars, where r bar is the mean of the residuals. More on that shortly. Of course, you could go all the way and look at standardized residuals as well. So notice now, in addition to the 1 minus h sub j square root, I have the square root of MSE and the square there. So then the question comes, well, what if normality does not? These epsilons have a normal distribution. What if, well, that's what we're assuming. What if then, well, that would mean that the y's don't have a normal distribution. What if constant variance doesn't hold? What if other violations of our stated model occur? Well, that means that any of the inference procedures that you looked at back in Stat 870 may not work. So that's why the Bootstrap is useful. Okay. Now, there's alternative ways to look at a regression model. And I failed to mention this before. Right now, I'm going to assume that the x's are constants. Okay? That's typically how regression is typically first introduced. But you could also assume that the x's are random variables with the y, so that x, y has a multivariate normal distribution to it. And basically everything just stays the same in terms of like the estimates and the variances. But you have to realize that now, instead of modeling the expected value of y, you're modeling the expected value of y given x. So you're conditioned on the value of x. In this kind of a setting, too, then one can derive that beta 1 would be, let's say, the covariance of x and y over the variance of x. And you can have a similar expression for beta 0 as well, just using properties of the multivariate normal. Then when you have that, then that allows you then to work with influence functions. And then obviously empirical influence values, and also the nonparametric delta method. You're not responsible for this, but one could show then that the empirical influence value for beta hat 1 is simply this. And that leads then to the nonparametric delta method estimate of the corresponding variance. Okay. So what you are responsible for is to understand, obviously, how to work with these empirical influence values. But let's say if I want to use a jackknife to estimate this LJ here, what would I do? Well, just like what we've done before. Okay, nothing really has changed. How would you use the regression method to estimate these LJs? Just like what we did before. Now we just have a different statistic that we're working with, beta hat 1. Okay. So there's going to be two different ways that we're going to look at for how to use the Bootstrap in a regression setting. In terms of, I should say, I'd be very careful when I say ways. I'm talking about two different resampling methods. Okay? Here's the first resampling method. It's called model-based resampling. It's going to be very similar to the semi-parametric models of sampling that we saw in Chapter 3. So let's say, again, here's our model. Y sub j is equal to beta 0 plus beta 1 times x sub j plus epsilon sub j. Now, the key thing to look at here is that these epsilon j's come from the same distribution. Okay? And if you wanted to, you don't even have to assume normality. normality. Just the idea that they come from the same distribution is what is important. Well, what we can do then is take advantage of that aspect. Why? Well, notice that the yj's themselves don't have the same distribution. For different values of x, yj's are going to have different distributions. But the epsilons all have the same distribution. So we can take advantage then of this basically the same way as what we did with the semi-parametric models in section 3.3. Where now what we're going to do is, you could say, resample your residuals. So if you remember how we looked at resampling stuff that was like residuals in section 3.3. Now, our book will call this a non-parametric bootstrap procedure, but I think that's, I don't know, I don't like that terminology. I guess I prefer to call it semi-parametric, because obviously you are assuming a particular kind of model structure. You'll see in our next resampling method, we probably won't get to today, but next week, that actually does not assume a particular model structure. And both of them will have advantages and disadvantages to them. So, I don't know, I'll go with the book and call this non-parametric, but I think it's more semi-parametric. Okay. So what we could do is resample the E sub j's. Simply take a y sub j, it's actually lowercase, y sub j minus beta hat 0 plus beta hat 1 times x sub j. We could resample those. But instead we're going to resample, as I alluded to earlier, these r sub j's. The reason being is because their variances agree with epsilons. Just reiterate something I mentioned earlier. Notice the variance of E sub j. It's not sigma squared. Epsilon, though, has a variance of sigma squared. What has a variance of sigma squared? Just deal with that hat matrix diagonal value part there, and now you do have a variance of sigma squared. So that's why we work with the r sub j's instead of the e sub j's. And we'll do one more modification, as I alluded to earlier, so that we have something that has a mean of 0. We're going to actually resample r sub j minus r bar. Now this r bar, the mean of all the r's, will be very, very close to 0, but it won't be 0 exactly. We'll just realize that. So it's a very minor modification, but this is what the approach of the book has done, and so that's why I decided to be consistent with what they do and do it as well. What do you think? Do you think the variance of this is still sigma squared? Actually, it's not. Unfortunately, the book doesn't really get into it very much, though. It's going to be very close to sigma squared, and we'll talk about it later on. Okay? So, what's y star then? Y star comes about the following way. You simply take beta hat 0 plus beta hat 1 times x sub j plus epsilon sub j, where these are resampled with replacement from the r sub j minus r bars. Okay? So form all that together, you get a y star. Now, an advantage of working with this approach is this. Each resample will have the same x's. Okay? So since we often refer to the x's in an x matrix as a design matrix, you could say then that our resamples each will have exactly the same design. Now, obviously in an experimental design setting that's important, but maybe not in every setting. But also let's think about another reason why this might be important. Let's say that your goal is to come up with a confidence interval for the expected value of y. Okay? And so what you're going to do is come up with let's say a mu hat or a y hat in the actual when you want to find a confidence interval. Now, let's say that your data for your x's in the original sample is between 0 and 4. But then when you do a resample and you didn't use the same x's, your data could be now, let's say, between there. So now and if you want to do this prediction at, let's say, maybe x equal 4, now you're extrapolating beyond the range of your data. So perhaps I'm getting a little bit ahead of myself here, but that's why this is a good approach for what we're doing here. We'll always have the same x's. You don't have to worry about ever having different x's so that you could potentially be extrapolating beyond the range of your sample values. Okay? Okay. Now for each resample, then you could estimate the model. Get like a beta hat 0 star, beta hat 1 star, get an S square star, as you might expect. How about we find some expected values, similar to what we first were doing back in Chapter 2. So let's see what the expected value star beta hat star 1 is relative to this resampling procedure. So as I indicated before, here's how this is beta hat 1 star. So let me just make sure, perhaps I don't need to do this, but I'm going to anyway. So remember I said this was beta hat 1. I took care of that wide bar there. Well, now for beta hat 1 star, it's exactly the same except for I have a yj star. Remember, the x's will always be the same. So what I can do is move then that expectation through the sum. Here's expected value star of yj star. Again, the x's are constants. Let's put in terms of what the model is, what this yj star is. So that's the next step. Beta hats are constants. The x is constant inside that expected value. So I can move the expected value through so that this part here just simply beta hat 0 plus beta hat 1 times xj plus expected value star epsilon star. And now let's just simply look at the individual terms that we get. So for beta hat 0, do all the multiplication, that's what we get. Same thing with the beta hat 1 times x of j, this is what you get. Of course, we can move the beta hats outside the sum. And then lastly, for the expected value star epsilon star, this is what you get. Everyone with me? Then we have some nice simplifications. Okay. Sum xj minus x bar is 0. So that goes away. The last term, expected value star epsilon j star, that's 0. Why? Well, remember what we're resampling. We resample with replacements. So every rj minus r bar has a probability of 1 over n being chosen. So here's my probability. I take it times the possible value that it can take on these epsilon j stars, just basically applying something we did in Chapter 2. Do a little bit of math, and you get 0, which makes sense. Another way you could have thought about it was, well, we know these rj minus r bars, the reason why we're doing the r bar there is that we have a mean of 0. So that's why that occurs. So here's my 0. So then that cancels out. And look what happens here. It drops out, and you're left with beta hat 1. So beta hat 1 star is an unbiased estimate of beta hat 1. That's a nice thing to have happen then for what we want to do. Note that I have put a proof like this on a test before. Okay. Well, what about then var star beta hat 1 star? So the variance. So let's just begin like what we did before. Write out what beta hat 1 star is, and then I push then the variance through the sum. Now, in order for me to do this, the yj stars need to be independent. Notice I have no covariances there. What do you think? Are they independent?
If you really nice data, they could be.
Well, let's think about how the yj stars come about. What do you think?
I'm sampling with replacement, right?
Yeah.
We should be
That's helpful, yes. But notice they're all sharing a beta hat 0 plus beta hat 1 times an x. So we'll assume that they're independent now, but I'll show you what happens in the end where it's not a big deal. Okay? Where it's not a big deal that they're actually dependent. Okay. Unfortunately, the book doesn't talk about it as much as it should. Okay. So let's then just simply write out what yj star is in terms of the model. And beta hat 0, beta hat 1, xj is a constant with respect to basically the distribution that we're working with here, the f hat distribution. So they disappear, those corresponding variances for those quantities, and you're just left with then the variance star of epsilon star there. Okay. Well, then we just use, well, what is the variance? Well, it's expected value star of epsilon j star squared minus expected value star of epsilon j star and whole quantity squared. We know that this expected value, though, is 0. We just found that. So then this variance is just simply the second moment. Well, how do we find expected values with respect to an f hat distribution? Again, you're taking the sum from j equal 1 to n, the probability of coming up with that particular item in your resample, times then what can these epsilon j stars be? Well, rj minus r bar squared. So we're doing the second moment. That probability here is 1 over n. So we're resampling with replacement. And so that's how I get then to this equality there. I think in the end this is just rearranging some stuff, so it's not a big deal. But look what happens. This cancels out that, and here's our variance. Well, how do we normally estimate this? Well, remember, sigma squared or the sum xj minus x bar squared. That's how we normally would estimate a variance of beta hat 1. I'm sorry, that would be the true variance, excuse me. Then we would estimate that by replacing sigma squared with MSE, the mean square error, or in other words, what our book would call S squared, which would be just the sum of the residuals squared divided by n minus 2. So then the question is, or what you would hope, I should say, what you would hope is then that this bootstrap estimate of a variance is similar to how we would normally estimate then the variance for beta hat 1. And in fact, they are close. They're not exactly the same, but they are close. But here's how you could make them exactly the same. Simply, remember these RJs are the residuals divided by 1 minus h sub j square root. Replace each of these h sub j with h bar. let's say. So notice now you don't have to worry about that j. You don't have to worry about them changing at all. And if you do that, you get this variance here then to be exactly the same as this variance here. Show that on your own. Just as a reminder, if it's been a while since you've taken a course in regression analysis, the sum of the h's here will be 2. It's just the number of parameters that you're estimating. So h bar then will be 2 over n. Okay. Well, what about then this independence of the y stars? We had to make that assumption in our little proof here. In the end, similar to what we said, is that we don't really have to worry about the fact that these are somewhat correlated because we are basically doing an IID sampling procedure here. The resampling, how we're resampling these, these RJs essentially. And we don't really have to worry about it unless n was small. But we can look into this a little bit further. And so, if you remember, let's see here. Let me give you a reference here on page 6.6. Oops, I lost all my page numbers. On 6.6, this next little things I'm going to do is deals with this here. In order to get this equality here, when I brought this variance inside the sum, so I can just put this right here, I'm basically assuming the covariances between, let's say, y1 star and y2 star are 0. Okay? So what would have happened, though, if I didn't make that assumption? So in other words, what I want to do is look a little bit more closely then into what is the variance star of the sum of the yj stars. This is now in 6.9. Okay. Well, I just write out the standard equation that we normally would have with the variances and the covariances. We know how to find these variances, okay? What we basically want to do is show that this part right here is going to be small. If it's small, then our derivations are pretty much okay. So let's look at these covariances. Let's just take a look at y1 star and y2 star. Equivalently, you're looking at the covariances between the epsilon 1 stars and epsilon 2 stars because all the other stuff in the y's are constants. So what is a covariance? Well, expected value star of epsilon 1 star times epsilon 2 star minus then, I guess, the first moments. These first moments are 0. So now you're just left with this joint moment here. Okay. What is this joint moment? Well, let's just go back to, just basic definitions of expected values now in the context of what we're doing here. And remember what we're working with here, these rj minus r bars. So just write both of them out. We have a 1 over n squared as well because of that sum. Well, what's going to happen as n increases? The covariance is going to go down. So that's why for a large sample size, or long as it's not a small sample size, it's not going to matter. And you often see this discussed too in a regression class when you're just doing regular regression analysis about the correlation amongst the regular residuals themselves, like E1 and E2. That you don't usually worry about that too much because it's going to go to 0. Okay. So, the reason why we first wanted to work with R sub j itself was because it has a variance of sigma squared. But in the end, for the actual resampling, we're working with Rj minus R bar. How does that really affect our stuff here? Does Rj minus R bar really have a, does that have a variance of sigma squared too? No. But it's close. So how would you actually find then what that variance is? Again, use the old formula that you're used to seeing. So variance of Rj plus the variance of R bar minus the covariance of Rj R bar. It's hard to say R bar. Anyway, I'll let you look at the derivation details on your own, and we will just focus on this right here, and then eventually this right here. So we would like this to be as close to sigma squared as possible. And notice the n here. So as n's getting big, as long as this stuff here is bounded, we're going to be okay. We're going to have a variance that's very close to sigma squared, as long as your sample size is not small. And so, what you can do is even use our big O or little o notation then to represent what we need this to be here. And this is not discussed in the book at all, and I didn't go through any more formal derivations to look at exactly what's happening with this term involving the hat matrix diagonal values and also off-diagonal values. But what I did was I looked at some simple simulated data sets and just to see, well, what happens to this quantity? And indeed, it is always bounded. It's not going off to infinity or negative infinity. And while that's not as good of a proof as I would like, I was satisfied with it. And so, yes, I'm okay with using Rj minus R bar. I'm going to have a variance that's close to sigma squared. But again, like I said, it's not discussed in the book, and I haven't seen it discussed elsewhere. Okay, so let's finally now get to an example so we can try some of this stuff out. So this is, I'm just going to try to reproduce the example that's in the book. It involves the mammals data set, where what we want to do is predict the brain weight of animals, or mammals, based upon their overall weight. So our X, or explanatory variable, is the overall weight of an animal, and the Y is their brain weight. Obviously, collecting this data was not beneficial to the animals. We have 62 different animals that sacrifice themselves for the research, I guess. Note here, I said I could not find this data set in the boot package. Actually, before class, when I was looking over my lecture notes, I decided to check to see if that was still true, and that is not true anymore. It is actually available in the boot package, but they have still forgot to put a help file associated with the mammals data set in the boot package. So if you just simply type mammals at a command prompt after you've done library boot, the data set will appear. So you don't need to download it from my website. So anyway, so this is what the data looks like. So for example, for the first animal, had a weight of 3.385. The brain was 44.5. Unfortunately, I don't know what the units are here. And also, unfortunately, it doesn't say what the actual animals were. But as you might expect, there's a variety of different kinds of mammals out there. Some are quite small, some are quite large. And so you would expect a lot of variability in what you see. So for example, we have a very large animal right here. And let's take a look at a plot then to take a look at the data and see how this variability affects the plot. So we could just do a simple scatter plot, as we've done many times before. And this is what's shown on the left-hand side here on page 12. And you can see, well, we have some animals that are really sticking out compared to the rest. And we have this clump of animals right here. This is a particular time where using a log transformation is often very helpful. So if I just simply use the plot function again and use log here for my x variable, log here for my y variable, and on page 13 you see a nicer looking plot. And you can definitely see a linear trend. Just a little side note, in the book itself, they do a plot similar to what I have on page 12, where they actually adjust the x-axis and y-axis scales to be on a log scale instead. If you ever wanted to do that in R, there's simply an argument in plot called log. Log equal xy does both axes. Do log equal x, you only do the x-axis, for example. Okay, so let's actually estimate the regression model. Who here has not used the LM function before? Thank you for being great.
I mean, not for, I looked at an example, but.
Well, I mean, I obviously I'm the only one here who teaches Set 870 who uses the LM function. So since none of you were ever in my 870 class in the past, I guess if you were in some of my other courses, I usually do a regression example at the very beginning. So like in 875, I do a regression example at the very beginning. So I guess that's how some of you have seen it. But anyway, let me just briefly talk about how R works in terms of regression analysis and the corresponding functions that are available to us. So the actual function, I guess you can say the equivalent of proc reg from SAS, the equivalent of that in R is the LM function. And notice how I specify my model. I did some poor syntax here. I should have said, to be more specific, formula equal, and then I can just simply say log of brain. Notice the log function does natural log by default. So I say log brain, and then I say tilde to separate the response variable from the explanatory variable, tilde log of body. So the nice thing is you can include transformations in there immediately. Just specify then where your data is, and then to summarize then the actual fit of the model itself, to get what you often see is the first page of a proc reg output, say summary of mod.fit. This is what we get. So we see here, for example, some information about my residuals. We have a table of estimates. So here's beta hat 0, beta hat 1. The std.error column is the standard error column, or in other words, the square root of the estimated variance of the parameter estimator. So 0.02846 is the square root of the estimated variance of beta hat 1. My t-value is, as you would expect, a t-test statistic to test whether or not that beta is equal to 0 or not. And then we have the corresponding p-value for a two-tailed test. So, is there evidence of a linear relationship here? Yes, there's strong evidence. And we saw that in the plot. One thing that I've always found interesting, R and its predecessor S+, you could say, basically assumes a little bit higher level of statistical knowledge than like SAS would, in terms of SAS gives you everything that you want, or everything and stuff that you don't want, where R usually doesn't give you everything that you want. You have to ask more of it. But I've always found it interesting how they have to put stars here to let you know, yes, this was significant. I mean, really, come on. I mean, people are going to know what that p-value is, and whether I have 1 star, 2 stars, or 3 stars, you don't need that extra part there. Anyway, maybe they just did that to help non-statisticians use R. So, residual standard error, this is my S, or in other words, square root of MSE. We have an R squared of 0.9208, so it looks like there's strong association there. And then your usual old F test statistic value as well, that tests the overall significance of the model, which in this case would be the same as just the t-test, since we only have one explanatory variable. Now there's actually a whole bunch more stuff inside of this mod.fit. And by the way, the reason why I use mod.fit, and I will always use that in this class, stands for model fit. You could call it something else where you save the results from the LM function. I just call it mod.fit. So names mod.fit allows you to see everything that's actually inside of there. So for example, mod.fit $ coefficients would be beta hat 0 and beta hat 1. Mod.fit $ residuals would be all your residuals. And you can look at some of the other ones on your own if you're interested. If I say ANOVA mod.fit, I get the usual old analysis of variance table as well. This F test statistic value here and the corresponding p-value will be exactly the same as what was in the summary output. And again, thank goodness we have those stars. Okay, so how can I get hat matrix diagonal values without actually having to do matrix algebra ourselves? Well, there's a function R called lm.influence, linear model influence. And if you've taken a full-blown Stat 870 class, you know there are tons of ways to measure influence or determine if you have outliers and stuff like that with respect to a regression model. And lm.influence just kind of puts a lot of these together into one function. And I'm going to put the results into something called influence.stat. And to pull the hat matrix diagonal values out of that, it's actually returned as a list. I can say $hat. With an object called h.j. To find my modified residuals then, I just pull residuals out of mod.fit and take the square root of 1 minus h.j. Again, taking advantage of how R does the vector calculations. So residual mod.fit $residuals is a 62 by 1 vector. H.j is 62 by 1 as well. And again, R matches everything up as you would like. My mean of these modified residuals, notice it's not 0. It's negative 0.00089. If I want to get my my square root of my MSC, or in other words, what R calls S, and put that in an object, what I can do is use, again, summary mod.fit, but now I'm going to save the results in the sum.fit. This is a list as well, and the key thing for us right here is that there's one part called sigma, and that will give you your S. Okay. So then my estimated regression model, of course, log of y, just don't forget the hat, 2.13 plus 0.75 times log of x. Notice we have a positive relationship, as you would expect. So as body weight goes up, brain weight goes up as well. Next, what I like to do is just recreate some of plots that were in the book involving the residuals. They did a QQ plot using a normal distribution, as you might expect. And so I'm going to do that here using, just our usual old code to do this. And then also they do a plot of these modified residuals versus the hat matrix diagonal values. Okay, so page 616 then. So here's our QQ plot. What do you think about normality? Yeah, looks decent. Yeah, we can't be too picky, but it looks really decent. Then they look at this right-hand side plot, modified residual versus H sub j. I've never seen a plot like that before, and it sounds like from the book that they're using this to assess non-constant variance. That there's maybe potential non-constant variance. Why? Well, typically the kinds of plots that we look for in these situations are usually your residuals versus your predicted value, your y hats, your mu hats, and you look for like a cone shape or basically some kind of change in the variability. But they're using this kind of a plot to make the judgment too. You can also get some other plots out from the results from the LM function. Remember that the plot function is a generic function in R, and there happens to be a method function called plot.lm. And this will automatically give you, if you use then the results from the LM function, this will give you up to 6 possible plots. And just to show you how it works, I'm going to say which plots I want plot 1 and 2. So I could have specified instead, use the C function, 1, 2 if I wanted to as well. And so here's where we get the residuals versus the predicted values, mu hats, y hats. And notice how, oops, I didn't draw that very well. Notice how the variability in the residuals kind of changes. It's not, what you usually think of as the cone shape that you're looking for, or a funnel shape. Instead, there's more variability in the middle than on the ends. Still, it's a sign of potentially non-constant error variance. And note that you can also get a QQ plot as well. We could do some histograms. We could do a histogram of our RJs. We can also do an EDF of the RJs as well. This is what we get. So, I also put a normal distribution overlay on the histogram. You might think there's maybe some problems there, but I don't know. I mean, histograms can somewhat be deceptive because, it depends upon where your classes are on your bars. And, I like the EDF plot. And that looks like normality works pretty well, kind of corresponding to our QQ plots. Okay, finally, let's do the Bootstrap. We're going to use R equal 999 resamples here. We need to come up with a calc.t function, similar to what we've done in the past. So, I call it calc.t.modbase to separate it from when we do this other resampling technique later. I'm going to pass in my data. This is actually going to be a vector of my rj minus r bar. Okay, so rj minus r bar. Eventually, that's what's going to be passed in there. I's, again, my indices as we've seen before. But then I have to pass in 2 other parts. My mu hat, or you can think of it again as your y hat. So you need the beta hat 0 plus beta hat 1 times x of j. You need all those to be passed in. Also, I need to pass in my x separately too. So first thing I do, I get what I call epsilon. This, these are not really epsilons. Eventually, when we do the resampling, there are epsilon stars, but I just use the name epsilon because it just makes sense. It's short. Then my y, which will eventually be my y star, is you take your mu hat plus epsilon. Then I need to estimate my mod. So again, I use the LM function with my y, which would be my y star with resample data, and my actual x's in the original order. Put then an object called mod.fit.modbase. I do a summary of the fit, where I put the results into a sum.fit.modbase. And then I tell R, what do I want to have passed back? I want the beta hats. So again, with resamples, this will be beta hat 0 star, beta hat 1 star. Remember, they are located in my $ coefficients part. I have the as numeric there just to remove some unneeded labels. And then I'm also going to pass back my S, which will be S star with resamples. So I guess I could do some of this directly here. So calc.t.modbase, data, rj minus the mean of rj's. Make sure I got rj already in here. So we're just trying it out. We'll do 1 to n. Notice where my mu hats are, or my y hats. They're in the fitted.values component of mod.fit. And then I pass in my x, which again is going to be, I chose to already do the log part there. So log of the body weights. So you got to be careful here that since we're doing the log transformation, we need to be realize that this x here is actually the log transform one. This y is essentially a log transform one as well. So let's go ahead and run this. Okay, I never set n. Sorry. That's what I get for not doing this interactively before. Okay, where's that? There we go. Okay. So here are my parameter estimates. They're the same, but it is the same as what we got with our original model. So on page 613, we have our beta hats listed there. Are they the same? Okay. Should we be worried? So normally, we run the calc.t function, and we try it out on our original data just to make sure everything's okay. Our statistic that we calculated always in the past should match up what we've calculated before if there may be similar means. Should we be worried? Oh, yeah, they're pretty darn close. But perhaps the way that I'm asking the question is that, no, we shouldn't be worried. You probably figured that out. Because remember, what we're passing in there, rj minus r bar. If we were passing in there e, then they will be the same. But we're not doing that. So that's something you got to be careful about, not to be alarmed that you're not going to get exactly the same value. But hopefully they should be close. And if they're not close, then that should be a warning to you, uh-oh, maybe my calc.t function is not programmed correctly.
Could you, as a test, pass through the
Yeah, I
E's
guess.
instead? Yeah.
Yeah, I guess I didn't think of that. But I mean, since we're always going to be working with this anyway,
Right.
that's why I did that.
Because those residuals are in your mod.fit too, right?
Okay, so I set a seed. Now I'm going to use the boot function. I'm going to save the results in boot.res.modbase. Notice what I have for the data argument, rj minus the mean of r.j. Here's my statistic, number of resamples, nonparametric sampling. I pass in there my mu hat and also my x's as well. So let's run this. And there we go. And notice how these estimates are exactly the same as what we had up here. Let me jump back over here to Word so I can mark on this. So we have bias estimates. We have a standard error estimate. So for example, this 0.0284, this is the square root of the estimated variance star beta hat 1 star. Let me put a little r here to emphasize that this is based upon 999 resamples. Now on page 13, we had found that the square root, the estimated variance of beta hat 1 to be 0.02846. Now what do you know? The Bootstrap is doing what we would hope it would do. Remember how we did that proof, too, to show what the variance would be. Again, the plot function is generic, so we can do some plots using the plot.boot method function. And by default, this is what will come up. Since the very first statistic that was passed back was beta hat 0, this is a histogram of all the beta hat 0 stars. We also have a QQ plot as well. What we would expect with a regression analysis is that these beta hats should have a normal distribution. It kind of looks like it. Then if I wanted to go to beta hat 1 and do exactly the same plot, I don't know if we've discussed this before, but what I can do is specify the argument index equal 2 to go to the second element of what's basically calculated by my calc.t. Again, I would expect normality, and it looks like we've got it. But remember, we didn't assume normality when we were actually taking the resamples itself. We're just assuming a particular kind of model structure, but not necessarily the actual distribution. And we also have then the plot for S star, square root of MSE. Note that this does not have a normal distribution. It shouldn't, or does not necessarily have a normal distribution because it's basically a variance estimate. But as we can see, normality seems to be a decent approximation here. Okay. So we can also do some additional calculations. How about if I find a standardized value, let's call it, or studentized value that we call in this class, a Z star. So this is just the usual old kind of Z statistic that you normally see, except for now I'm calculating with the resamples instead. How do I do some of these calculations? For example, to get the sum of the xi minus x bar squared, I just simply use the var function multiplied by n minus 1. That's my sums of squares for the x's, or it's often referred to as SSX. And the other stuff's pretty much self-explanatory. Now, in a non-bootstrap setting, if I just had z up here instead, this should have a approximate normal distribution to it, right? Okay. It's actually a t distribution, but if you have a large sample, it's going to be a normal distribution. So it's doing a normal distribution comparison here. So how about if I look at these z stars, get the 0.05 and 0.95 quantiles out? This is what I get. What is the actual quantiles from a standard normal? Pretty close. Again, it's nice that this is happening. It's just, this is kind of, by example, showing the Bootstrap is doing what it should be doing. Now, I have no other calculations done for this problem, but you need to know, make sure you do this, is to figure out, well, how would you find a confidence interval for beta 1 here? I guess we have a few minutes so we can talk about it. How would you do that? What would you do next now that we have this stuff from the boot function? What function would you call next? Boot.ci, exactly. Pick your favorite Bootstrap confidence interval method. Hopefully it's BCA or studentized, and use that. You get a confidence interval for beta 1. How about, because remember beta 1 is the second, or beta hat 1 is the second element returned by my calc.t. So that's why I can do that easily. So of course when you use the boot.ci function, you need to say use the second element. How about a confidence interval for the expected value of y? So for this confidence interval for beta 1, remember we have beta hat 1 that's returned to us from calc.t. So that means we're going to have to probably modify our calc.t function, right? What would you want returned? Yeah, corresponding y hat. Now actually in this particular case, since we returned beta hat 0 star and beta hat 1 star, outside of, right now we have enough information where we can just simply say, let's take all my beta hat 0s plus beta hat 1s times the corresponding x that I'm interested in, and I could do this outside my calc.t. Or alternatively, you can have calc.t, and maybe you're only interested in this confidence interval. We're not interested in confidence interval for beta 1 itself. You can write your calc.t function so that it only returns your y hat at the specific x that you're interested in. Once you get these y hats or y hat stars, or I guess, sorry, mu hats and mu hat stars, what would you call next for a function? We've got CI. There you go.
If we calculated it out, those mu hat stars in the space outside of our calc.t function to calculate our CIs, we have standard errors and things. Can we get to a confidence interval without doing it in a calc.t and using boot.ci?
You could. But you're going to, you're just not going to be able to use boot.ci. You could probably get around with using boot.ci. Here's a quick little trick. Let's say that you have the results, just be generic, you have the results in boot.res from using boot. Now remember, this is a list, and it has one component called t. Okay? Just change the t. So, let's say outside of calc.t, that's where you do the y hat calculation, get the y hat stars, make those, this is kind of pseudocode, do that. That makes sense? That's a quick way that you could do that. How about a confidence interval for x? Do an inverse prediction. What would you do? You remember doing inverse prediction? No, simply your calc.t function, get x hat. Okay? It's a simple formula. Get x hat so that that's passed back from using calc.t and then use a boot.ci function. So it's just kind of an application of all the stuff that we did before, but now we just have different statistics, different parameters, so that's why I chose not to go over the details. But be ready for something like that on the final exam. So there's some other stuff in this section you're welcome to take a look at, in particular the parametric bootstrap. You should think about how you would do this parametric. The same extension to this from the stuff that we've done before would occur here. Okay, so we are out of time. Are there any questions? Okay, so test next time, and then on next Tuesday we will talk about the second way to do resampling with respect to the regression model. This is actually a little bit easier to do, but it has, again, pluses and minuses compared to this model-based resampling. So that's it for today.